Hey everyone, I hope you're all doing well. Today we're going to continue our discussion of electrons and their energies. So last time we were discussing shells, subshells, and atomic orbitals, and we saw that atomic orbitals show us approximately where an electron is in an atom, because according to the quantum mechanical model, we can't know for sure where an electron is at any point in time, but we can narrow down a location or a probability of where an electron is. Now, to continue our discussion of atomic orbitals, according to the quantum mechanical model, all types of atomic orbitals can contain a maximum of 2 electrons. So down below in our chart, if we look at the 1s orbital, that can hold 2 electrons. So I'm just going to put a 2 and a little electron symbol next to it. Now, a p orbital can also contain 2 electrons, but remember that a p subshell has 3 orbitals. So we can have a maximum of 6 electrons in that p subshell. And then in a d orbital, we can also have a maximum of 2 electrons, but in a d subshell there are 5 atomic orbitals. So that means that a d subshell can hold a maximum of 10 electrons. And then in an F subshell, we have 7 atomic orbitals, and each one can hold 2 electrons. So then we can have a maximum of 14 electrons in an F subshell. Now, again, these are just maximum amounts. We could have less than that in our subshells. It just depends on how many electrons an atom actually has. So now if we look at each energy level, in energy level 1, we can have a maximum of 2 electrons. In energy level 2, we have an s orbital and 3 p orbitals, and each one can hold 2 electrons. So that means we can have a maximum of 8 electrons in energy level 2. And then in energy level 3, we have an s orbital, 3 p orbitals, and 5 d orbitals. So if we add those together, we have 2 electrons in an s orbital, a maximum of 6 electrons in the p orbital, and then a maximum of 10 electrons in the d orbitals. So that would give us a maximum of 18 electrons in energy level 3. And then in energy level 4, we can have 14 more electrons. So let's see, 18 plus 14. So that would be, oh man, it's too early to do math today. So we'd have 32 electrons. I need more coffee. Okay, so those are the maximum number of electrons that we could have in each energy level. And these different subshells and atomic orbitals, they all have different energy levels because remember that an s orbital is lower in energy than a p orbital, and then d and then f follow. But then additionally, energy level 1 has less energy than energy level 2, etc. So we get this energy diagram off to the right, and you can see that the 1s orbital is really low in energy. And again, that's because it's closer to the nucleus. So the closer an electron is to the positively charged nucleus, the more stable it is, and the less energy it has. Then the next orbital is the 2s orbital, And then within that same energy level, we have a 2p orbital, or 2p subshell. So that's going to be a little higher in energy than a 2s orbital, because s orbitals are lower in energy than p orbitals. And then we go to energy level 3, where we have the 3s orbital, the 3p orbitals, and the 3d orbitals. So you'll notice that they're ranked in order of energy, so S is lower than P, which is lower than D. Now, one tricky thing is you'll notice that the 4s orbital is actually lower in energy than the 3d orbitals. So this goes kind of out of order of what we would expect, but scientists found that electrons would prefer to be in a 4s orbital rather than a 3d orbital most of the time. So that tells us that a 4s orbital is actually a little bit lower in energy than a 3d orbital. Now, you don't necessarily have to remember that. We'll talk more about these energies later on. Okay. So, in your textbook, there's a table, table 3.1, and this summarizes all of the information we covered. So you'll notice in the first column we have the shell number, or the energy level. So I'll put energy level down here. And then in the second column, we have the number of subshells in each shell. So remember that the number of subshells is equal to the shell number. And then next to that, we have subshell designation. So in, let's see, shell number 1, we have 1 subshell, and we would call that a 1s subshell. And then in, let's see, let's jump to shell number 4. We have 4 subshells, and we would designate those 4s, 4p, 4d, 4f. And then we have next to that the number of orbitals in each subshell. So we said that s orbitals have s subshells have 1 atomic orbital. Even I'm getting a little mixed up here. So if you feel confused, it's okay. I've just been doing this for many years and still get them confused. Let's see. And then in energy level 2, we have, again, a 2s subshell and a 2p subshell. And s subshells have 1 orbital, and p subshells have 3 orbitals. And then as we continue, again, we can see that in a d subshell, we would have 5 orbitals, and in an f subshell, we would have 7 orbitals. All right, and then let's jump over a couple of columns, and we can see that the maximum number of electrons in a subshell is listed. So each s subshell has only 2 electrons maximum. Each p subshell can have 6 maximum electrons. Each d subshell can have 10 maximum electrons. And then that f subshell can have 14 maximum electrons. So then in the final column, we have the maximum number of electrons in a shell. So in shell 1, we have 2. In shell 2, we can have 8 maximum electrons. In shell 3, we can have 18 maximum electrons. And in shell 4, we can have 32 maximum electrons. So hopefully seeing this table helps a little bit, especially if you didn't quite understand the number of electrons that I mentioned earlier. Now, let's say that we have an atom with a particular number of electrons, and we're trying to determine where those electrons exist. What we're going to do is we're going to say that electrons are filling subshells in the order of increasing energy. So we're going to fill a 1s subshell before we fill a 2s subshell, because remember the 1s subshell is lower in energy than a 2s subshell. And down below there's a nice easy way to remember the order for how to fill orbitals. So you can write out a chart like the one on the left. So we have all of the s orbitals in a column. And we're going to write all the way down to 7s because we have 7 periods. And then in column 2, we have all of our p orbitals, or subshells. And then in the third column, we have all of the d subshells. And then in the fourth column, we have the f subshells. Now, there are more than these subshells, but we're just going to stop there. And in our class in particular, we're really just going to focus on the first few rows of elements. So you don't really have to worry about, for instance, row 5 and beyond. Or even really row 4. Okay, so let's look at the diagram on the right. We can draw arrows going through each of these different subshells, and you can see that we would fill the 1s subshell first, followed by the 2s subshell, then the 2p subshell, then the 3s subshell, then 3p, then 4s. Remember, there was that little trick. 4s is lower in energy than 3d. So 3d would come next, then 4p, and then 5s comes next. So that's another tricky thing. And then we would keep going. But again, you don't really have to know the order beyond maybe 3d. All right, now there are a couple of rules we have to follow when we're filling in electrons. So the order of subshell filling must obey Hund's rule and the Pauli exclusion principle. So let's talk about those two rules. And again, it's okay if you're confused. We'll go over a couple of example problems in a bit. Okay, so according to the Pauli exclusion principle, only electrons spinning in opposite directions can occupy the same orbital within a subshell. So one interesting thing about electrons is they kind of act like magnets. They do spin as they're moving, and as they spin, they're generating a magnetic force or a current. And so if an electron is spinning in one direction, then, for instance, its magnetic field will point up. And if an electron is spinning in the other direction, its magnetic field will point down. So you can see here we have an electron whose magnetic field points up. And then over here we have an electron whose magnetic field is pointing down. Now, in order to exist in the same atomic orbital, electrons have to have opposite spin or else they're going to repel each other. And this is true of magnets too. If you've ever tried to put the north end of one magnet facing the north end of another magnet, they're going to repel. But if you put the north end of one magnet pointing towards the south end of another magnet, then they attract. So electrons, because they're all negatively charged, they traditionally are going to repel each other anyway. So in order to ease that, you're going to pair up two electrons that have opposite spin, because then at least they're not going to totally repel each other. Now, we're also going to indicate these different electrons and their spins with arrows. So up above, you can see that we're going to show one electron as an up arrow and another electron as a down arrow. So off on the right, we have a diagram of different elements. So hydrogen has one electron. So we would start filling in our energy diagram that we saw earlier, and we would just put one electron in the lowest energy orbital, which is the 1s orbital. And we can actually show that as either an up arrow or a down arrow. It doesn't really matter, but typically chemists will show an up arrow first and then a down arrow second. And that is shown in helium. So helium has 2 electrons. So we're going to show that one of those electrons is spin up and the other one is spin down. So we've got an up arrow and a down arrow. Now, remember that s orbitals can hold a maximum of 2 electrons. So if we have an element with more than 2 electrons, we have to put the 3rd electron in the next highest energy orbital. So lithium, for instance, has 3 electrons, and we would have 2 electrons in the 1s orbital, and then 1 electron in the 2s orbital, which is the next highest orbital. Now, remember, you can determine the number of electrons for an atom, because that's going to equal the number of protons, and that equals the atomic number. So if you're ever in doubt about how many electrons an atom has, you can look at the atomic number. All right, and then the other rule, Hund's rule, electrons will not join other electrons in an orbital of a subshell if an empty orbital of the same energy is available in the subshell. So this is a long way of saying that electrons would prefer to be in their own orbital, because remember, electrons are all negatively charged, so they naturally do want to be far apart from each other. But if they're forced into the same subshell, they should have opposite spin. So let's write electrons prefer to be alone if they can. So for instance, if we have the element carbon, carbon has an atomic number of 6. So that means that it has 6 protons and 6 electrons. So now let's figure out where those electrons are located. So we're going to start at the bottom of this energy diagram. So we're going to fill in the 1s orbital with 2 electrons. We've got an up arrow and a down arrow. And remember that each orbital can only hold 2 electrons or less. So we've used up 2 electrons, so the next 2 electrons will go into the 2s orbital. Okay, so we've got 4 electrons. Now we have 2 left. So we're going to start filling in the 2p orbitals next. Oh, I gave away the answer. No. So we're going to put 1 electron in the first orbital. And instead of pairing the electrons, remember electrons would like to be alone if they can. So in this case, there are 2 other orbitals in the 2p level. So we can put an electron by itself in the next orbital. And again, this is Hund's rule. So this would be our energy diagram or orbital diagram for carbon. Okay. So remember, if you have multiple orbitals that all have the same energy, similar to our 2p orbitals, electrons would like to have their own orbital, or kind of like their own room, rather than share a room with another electron. So if you have siblings, for instance, maybe you love your siblings and you want to share a room with them, but most often I think people would prefer to have their own room, and that's the same with electrons. Okay, and then here's the answer slide, which I gave away earlier. All right, so now when it is remembered that each orbital of a subshell can hold a maximum of 2 electrons, and that Hund's rule and the Pauli exclusion principle are followed, the following filling order for the first 10 electrons looks like this. So we already talked about hydrogen, helium, and lithium. So let's look at beryllium. So beryllium has 4 electrons because its atomic number is 4, and its orbital diagram looks very similar to lithium's, except we have 1 extra electron in the 2s orbital. So now we have 2 sets of paired electrons. All right, and then we're going to jump to boron, which has 5 electrons, and the next highest energy subshell is the 2p subshell, so we'll start filling that in with 1 electron. And then carbon we already went over, so we would have 2 unpaired electrons in the 2p subshell. And then nitrogen would have 1 more electron than carbon, so we would put that next electron in its own orbital. And then when we get to oxygen, now we have 8 total electrons from oxygen. So now that 8th electron doesn't really have anywhere else to go, so it has to share an orbital with one of those electrons. So we're going to pair that 8th electron, and it will be spin down so that the 2 electrons will actually stay in the same orbital together. And then fluorine has 1 more electron than oxygen, so we're going to pair that electron. And then neon has yet another electron, so we'll pair that up with the last remaining unpaired electron. Okay, so hopefully you're starting to see the pattern here. And again, this is just telling us the probability for where an electron might exist. Now, instead of having to draw these orbital diagrams each and every time, we can summarize the location of electrons using what are called electronic configurations. So electronic configurations give details of the arrangements of electrons in atoms. So the notation that's used is, for instance, 1s2, 2s2, 2p6, and we would keep going depending on how many electrons we have. So the occupied subshells are indicated by their number and letter, such as 2s, and then the number of electrons in the subshell is indicated by the superscript on the letter. So for instance, if we say 2s2, that means that we have 2 electrons in a 2s subshell. So down below, we can see hydrogen and helium. And again, hydrogen has 1 electron, and that 1 electron is in the 1s orbital. So the electron configuration for hydrogen would be 1s1. And then for helium, helium has 2 electrons. So its 2 electrons are in the 1s orbital, and we would write the electron configuration as 1s2. And then we would keep going from there. So lithium, we said, had 3 electrons, and its 3rd electron goes into the 2s orbital. So its electron configuration would be 1s2, 2s1. And we would just keep going as we add more and more electrons on. So earlier we saw the example of carbon, and we saw that there were 2 unpaired electrons in the 2p subshell. So we would write the electron configuration as 1s2, 2s2, 2p2. You might also notice that if we add all of the superscripts together, that gives us the total number of electrons. So let me rewrite carbon's electron configuration. And again, if we add together those 3 superscripts, so 2 plus 2 plus 2, that gives us 6 total electrons. So for instance, let's say I gave you an electron configuration and I asked you to determine which element corresponds to that electron configuration. You could always add together the superscripts to determine the number of electrons in that atom. And then you could look on the periodic table and find that atomic number. And that will help you identify the element. All right, so now let's go down the chart to neon. Neon has 10 electrons, and they're all paired. So we're completely filling in the 1s, the 2s, and the 2p subshells. And its electron configuration is 1s2, 2s2, 2p6. Because we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 6 electrons in the 2p orbital. Now, what's really interesting is that the order of subshell filling matches what we call subshell blocks on the periodic table. So this is our periodic table down below. And let's see, so on the left-hand side in yellow, we have what's called the S block. So we've got hydrogen, helium, so helium's been moved over. And then we've got lithium, beryllium. Then we jump over to what's called the P block, which is in green. And we have boron, etc. And then at the end we have neon. So as you're filling in electrons, you can also kind of figure out which blocks are getting filled in. So for neon, for instance, we just said that its electron configuration is 1s2, so we completely filled in that 1s block, and then followed by 2s2, so we completely filled in the 2s block, and then we have 2p6, so we completely filled in the 2p block. So that's another way to kind of think about the order of filling for electrons. Now in row 4, you'll notice that the 4s comes before 3d. So that still holds true according to the energy ordering of subshells. And then after that, we would start filling in the 4p electrons. So again, just another way to kind of visualize where electrons exist. So let's actually go over an example where we're going to write the electronic configurations for each of the following elements. Okay, so magnesium, silicon, iron, and gallium. Now, magnesium, if we look at a periodic table, has 12 electrons. Okay, so we're going to fill in these 12 electrons and figure out where their electrons exist. Okay, so remember that we want to fill in the 1s orbital first. So we're going to start by writing 1s. And the 1s orbital can only contain 2 electrons. So we have 1s2. And then we're going to fill in the 2s orbital, which comes next, and that can also only have a maximum of 2 electrons. And then next is the 2p orbital, and that can hold a maximum of 6 electrons. So what's great about this is once we've completely filled in the 1s, the 2s, and the 2p orbitals, that means we have 10 electrons. So that's a good stopping point if you ever need to determine how many electrons you have. Now, magnesium has 12 electrons, so we have 2 more electrons that we have to fill in. And the next orbital, according to our chart below, is the 3s orbital. And that can hold a maximum of 2 electrons. So that works out. We have 1s2, 2s2, 2p6, 3s2. So that is the electron configuration for magnesium. Now, if we actually go back to the chart that we were just looking at, magnesium is right here on the periodic table, and you'll notice that we completely filled in the 1s block, the 2s block, the 2p block, and the 3s block. Okay, so the next one is silicon. So on the periodic table, silicon has an atomic number of 14. So it has 14 electrons. So the electron configuration for silicon will look pretty similar to magnesium's, except we'll have 2 more electrons. So that means that we are filling in the 1s orbital, the 2s orbital, the 2p orbital, and the 3s orbital. So that's 12 electrons, and now we have 2 more. So what comes next? We stopped at the 3s, and according to this chart, the next orbital that we need to fill in is 3p. So we'll put 2 electrons in the 3p subshell. Now remember that the 3p, or really any p subshell, can hold a maximum of 6 electrons, but you can also have less than that. So we could just have 2 electrons in that p orbital or subshell, and that's fine. Now, in that 3p subshell, remember that the electrons will be unpaired initially, and then if we keep adding more and more electrons, so let's say we had, we were filling in the orbitals for argon, which has 18 electrons, then we would start pairing electrons once we have 3 unpaired electrons. So let's look at iron. So this one will be a little bit trickier. This one's a bit of a challenge problem. So on the periodic table, iron is in the transition elements. So it's in the middle. And it has 26 electrons because its atomic number is 26. All right, so let's start filling in those orbitals. So again, we start with 1s, followed by 2s, then 2p. So remember, if we have 1s2, 2s2, 2p6, that's 10 electrons. Okay, so we have 16 electrons left. So now we have 3s2, and then we're going to completely fill in the 3p subshell. So let's see, that's 2 plus 2 plus 6 plus 2 plus 6. So that should give us 18 electrons that we've used so far. Now, if we've filled in the 3p subshell, the next one is 4s. And that can only hold a maximum of 2 electrons. So we've got a total of 20 electrons right now, and we need to fill in 6 more. And I'm just going to erase this drawing to make some room. So after we filled in the 4s subshell down below, we can see that the next one we can fill in is 3d. Now remember, d subshells can hold a maximum of 10 electrons. But so far we have 20 electrons, so you can add together those superscripts. So we need to place 6 electrons in the 3d subshell, which works out because we have less than the maximum. So this would be our electron configuration for iron. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So this is a long electron configuration, and in a bit I'll show you how you can abbreviate the electron configuration even further. All right, so let me just erase this down here to make some room for gallium. So if we look up gallium on the periodic table, gallium has 31 electrons. So it has 5 more electrons than iron. So that means we're probably going to have a similar electron configuration. So let's just rewrite those first set of subshells. Okay, so we said that when we have this particular electron configuration, there are 20 electrons. So we need to fill in 11 more electrons. So if the next orbital is the 3d set of orbitals, remember that d subshells can hold a maximum of 10 electrons. So let's just fill in that 3d subshell with 10 electrons. So now we have 30 electrons, and we need to put the last electron. Let's see, so down below after 3d comes 4p. So we'll just put that last electron in the 4p orbital. All right. And if we go back to the previous slide, gallium is right here on the periodic table. So we can see that we've completely filled in 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then we have our last electron in the 4p orbital. Okay. So hopefully that helps a little bit with seeing how we write out electron configurations. And again, this just tells us where electrons are located around a nucleus. So we can also see the different energies that are associated with these electrons. So some electrons are higher in energy than others, but they always fill in from lowest energy to highest energy orbitals. And then here's that solution slide if you need that later. And finally, we're going to talk about noble gas configurations. So this is one way that we can abbreviate an electron configuration. So with the exception of helium, all noble gases, so those are in group 8A, they have electronic configurations that end with completely filled S and P subshells of the highest occupied shell. And these configurations are called noble gas configurations. So what we can do is write electronic configurations in an abbreviated form in which the noble gas symbol is enclosed in brackets and is used to represent all electrons that are found in that configuration. So let's look at some examples down below. So we know that helium's electron configuration is equal to 1s2. So we saw that earlier. And we can actually show helium in brackets, and we can substitute that in, for instance, for lithium. So lithium's electronic configuration is 1s2, 2s1, which we saw earlier. But instead of writing 1s2, we could just put in helium in brackets. And then we would follow that with 2s1. Now, we also saw earlier that neon has an electron configuration of 1s2, 2s2, 2p6. And that's because neon has 10 electrons. So we could put, for sodium, instead of 1s2, 2s2, 2p6, 3s1, we could substitute neon in for the first 3 subshells. So then we would have neon in brackets followed by 3s1. And that's much easier and simpler to write than the full electronic configuration. Now, for potassium, I'll just show you that the noble gas that comes right before potassium is argon. So this is in the row above potassium's row. And argon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So we could substitute part of potassium's electron configuration with the configuration of argon. So we end up with argon in brackets followed by 4s1. And then rubidium, we can replace the majority of its electron configuration with krypton in brackets. And you'll notice on a periodic table that krypton comes right before rubidium. So it's in the noble gases in the row above. Okay. So remember earlier we wrote out the noble gas configuration, the electron configurations for magnesium, iron, and gallium. But let's write the noble gas configurations for these elements. So we said that magnesium's electron configuration was 1s2, 2s2, 2p6, 3s2. Now, if you have your periodic table handy, you'll notice that if we go up a row and over to group 8A, the noble gases, the noble gas that comes before magnesium is neon. So remember that neon's electron configuration is 1s2, 2s2, 2p6. So we can substitute neon in for part of magnesium's electron configuration. So we would have neon in brackets followed by 3s2. And then I'll use a different color for the next element, which is iron. Oh, giving away the answer again. So remember that iron's electron configuration was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So that takes forever to write out. So instead of writing all of that out, let's find the noble gas that comes right before iron. So if we go up one row and over to the noble gases, we have argon. So argon's electron configuration, we said, was 1s2, 2s2, 2p6, 3s2, 3p6. So now we can replace the majority of iron's electron configuration with the noble gas. So we'll put argon in brackets, followed by what's left over, which is 4s2, 3d6. And now for gallium. So gallium had an electron configuration that was pretty similar to iron's, but it has a few more electrons. So I'll just rewrite that here. Oh, that's a long one. Now, the noble gas that comes right before gallium in the row above is argon. So remember, again, argon completely fills in the 1s, the 2s, the 2p, the 3s, and the 3p subshells. So we can just substitute in argon, followed by 4s2, 3d10, 4p1. And that is much easier to write. Okay, so here is the solution slide for those three elements. And again, the reason we use noble gases for these abbreviations is because they do completely fill in their particular set of orbitals. So it's just kind of a handy way to abbreviate electron configurations. All right, so we're going to stop there. This was a bit of a longer video, and I will see you in the next video.